So this equals, so I'm going to, excuse me, take off the n plus first term. So this is going to be
a to the n plus 1.
Yeah, so we're going to get, n choose n, right? A to the n plus 1, b to the n plus 1 minus n plus 1, which is just a to the n plus 1. So that equals a to the n plus 1, right? Which actually should make you feel really good, because that's actually the first term when you write the binomial theorem, right? The first term is always a to the n plus first power or b to the n plus first power, depending which way you go. So then I'm going to add to that the remaining terms, k equal 1 to n of n choose k minus 1, a to the k, b to the n plus 1 minus k. And now I'm going to throw away the 0th term here, so I'm going to get sum from k equal 1 to n. So now I have the same limits. N choose k, a to the k, b to the n plus 1 minus k, plus, similarly, this is b to the n plus 1. And now everything, these two parts are the same. So the distributive law tells me that when I combine these, I'm adding those two terms. So this now equals a to the n plus 1 plus the sum from k equal 1 to n of n plus 1 choose k, a to the k, b to the n plus 1 minus k, plus b to the n plus 1. But you recognize, again, this is the first term of the binomial. This is the 0th term, and this is the n plus first term. So this then is just the sum from k equals 0 to n plus 1 of n choose k, a to the k, b to the n plus 1 minus k. What did a plus 1? Yep. And that's it. You need to work through this proof, okay? Because again, there are some very important things in here. The main one being the index shift, right? And again, if you're interested in computer science at all, I mean, this is the kind of thing, you know, when you have counters in computer science, you often have to deal with this sort of thing, all right? So you need to be good at it. Be a useful thing in the future. Okay, so that's the binomial theorem. We'll wrap up now with just a couple of simple applications. So to start with, let me just start writing out some terms. Okay, so a plus b to the n, this equals a to the n. Okay, what's the second term? It's always n choose 1, which is n. And this term?
A to the n minus 1.
Yeah, so let's actually, so we actually need to start, yes, 2, but we're going to have to reverse the b's and the k's, right? N of n choose k, a to the n minus k, b to the k. See why I reversed those, right? Because in this case we started with a to the n, so we're counting down with the a's, and so that's why the a has to have the n minus k. Okay, well this then in fact is bigger than or equal to a to the n plus n a to the n minus 1b, provided. So how did I go from here to here?
You assume that sum is greater than or equal to 0, right?
Okay. If I have this, that means I have to be assuming that this term is bigger than or equal to 0, right? So what's pretty much the only thing that's going to guarantee that that's true. Yeah, or non-negative, right? Provided A and B are bigger than or equal to 0. And of course, we also need that n is bigger than 2. Otherwise, we don't have bigger than or equal to 2. Otherwise, you don't have any terms to throw away. Okay, so this is a simplifying factor, okay? If you've got something and you're just trying to estimate what it is, this tells you that if this is going to be small, and there may be reasons why you know that, then you can simply throw that away. Okay, so basically, with an inequality, you can simplify down to this when that's appropriate, okay? And you may not be able to think of times right now when that is appropriate, but it is. Okay, so this is something that you get out of the binomial theorem, and you know, you could try to prove this by induction, right? That this is bigger than or equal to that. Okay, I don't encourage that. In fact, there are a lot of things, anything which follows in a non-trivial way from the binomial theorem, be very careful about trying to prove it using induction. Because if you look at how long the proof of the binomial theorem is, if you don't use it, you may end up doing a lot of that work. And that would mean having to discover exactly how to do that work in the context of the proof, and that's probably, you're probably not going to have much time for that, right? So when you have a theorem, use it. The other thing you can do with the binomial theorem is you can just play games with actually with specific numbers, okay? So 2 to the n, well, that's 1 plus 1 to the n, right? But what's that equal to then? Well, we're going to get the sum from k equals 0 to n of n choose k, right? Times 1 to the k times 1 to the n minus k, which is just what? So this is kind of an interesting fact. I don't know whether you'll ever have any use for it, but it tells you that if you add up across, right, you fix n, you add up across any row in Pascal's triangle, you always get 2 to the n. Okay, again, not obvious from looking at Pascal's triangle, but the binomial theorem makes it a very, very, very simple statement. Okay, it's break, so we'll finish 7 minutes early, so you guys can get started and have a good break. I will assign, oh, and you have homework, sorry, and yeah, and I have to finish all this grading over break, and I have 2 conferences that I'm organizing, so that's going to be exciting. Okay, but anyway.